Thanks everyone for joining us, especially people who joined our informal gathering. That was nice. So first we've got Dennis. Dennis is a graduate from the University of Pittsburgh, but he's been living and working in Western Siberia for the last 3 years. In addition to quaternary paleo-environmental reconstructions, he has a strong interest in Bronze Age archaeology. Today he'll be talking to us about Northwest Siberia as a desert. Go ahead.
Okay, thank you, Lauren, for this introduction. Okay, so today I will talk to you guys about our research. It has recently been published in Quaternary International. The title of the article is Northwest Siberia as a Mist-2 Desert with a question mark, Inferences from Quartz Morphoscopy and Polygonal Ice Wedges. So I'm the second author on this article, and I was largely responsible for the morphoscopic analysis. I'm a research associate at the University of Tyumen. Tyumen is the name of a Russian city. It's known to be the sort of administrative center for various oil and gas extraction operations. And here on the map in red, you see the extent of the Tyumen district. So the research question that we were faced with was, what was the environment like in Northwest Siberia during Mist-2, marine isotope stage 2 period? It is also known as the last glacial maximum, or the Sartan cryochron, lasted roughly from 28,000 to 11,000 years ago. So this question has actually been debated quite a bit in the literature. Earlier and up through the 1990s, it was thought that this region that you see on the map that's on the slide, that it was all covered by a huge glacier. And it extended all the way south to the Siberian Urals. Siberian Urals is this low elevation upland, ranges from about 100 to 300 meters above the sea level. And it was previously thought that this was a moraine associated with this huge glacier. And recently this idea has been overturned. And what came to replace it was this view of Northwest Siberia being a cold, arid, sandy desert that began forming in the first half of Mist-2, and with the peak of aridization falling on the second half of Mist-2. The problem with this desert hypothesis is that our research team, as well as other researchers, repeatedly find these polygonal ice wedge pseudomorphs all over Northwest Siberia. These ice wedges, polygonal ice wedges, I'm sure a lot of you have heard about them, but they form in low temperatures in areas with little vegetation and little snow cover. And when they melt, they get filled in by whatever material is on the surface at the time, forming what's known as a ice wedge pseudomorph. And so these pseudomorphs in Northwest Siberia, they lie just below the Holocene soils. So it is generally believed they date sometime to the Mist-2 period that preceded the Holocene. And the interesting thing about these pseudomorphs is we repeatedly find paleosol inclusions, so inclusions of ancient soil, remnants of plant debris, and also gleic and ferric pedosediments that indicate that these surfaces were water saturated. So these things kind of indicate there were some, some plant life, there were soils and water saturation on these surfaces during Mist-2. And all of these things contradict the sandy desert idea. So to investigate this question further, we've analyzed materials that came out of 3 cross-sections that we placed in different subregions of Northwest Siberia. You see them marked as red dots on this map. You see the locations of the cross-sections. I won't confuse you with all of the names, but each section contained ice wedge pseudomorphs. And we've taken 2 samples from each section, one from the wedge field and one from the surrounding or host sediment. And the chronology of these features, the general chronology is such that whatever is in the wedge dates to the second half of the MIS2 period. And you see the dates on the slide, roughly from 17 to 11.7 thousand years ago. And whatever is in the host sediment, that formed earlier. So that dates to the first half of this cryochron. So from 27.8 to 17,000 years ago. And this chronology is based on years of observations, stratigraphic observations, and also on radiocarbon dates that I will talk about in just a minute from these cross sections, and also from similar features that we've observed over the years all over this region that have previously been published. So the methods that we've used radiocarbon dating wherever we could, because there isn't that much organic material in these sandy sediments. But we were able to obtain 2 radiocarbon dates from the Paleosol inclusions that we found inside of the wedges. And they gave us pretty close dates, 13.5 to 13,000 years ago. And that tells us when these ice wedges were melting and getting filled in by whatever material that was on the surface. And besides these Paleosol inclusions, we found glaic and ferric petal sediments that you see on this right-hand upper picture as these sort of rusty colored brims and rusty colored inclusions inside of the wedge. And again, they tell us about water saturation. And the main method that we relied upon in this analysis was quartz grain morphoscopy. And it consisted of 2 stages. The first stage involved an optical binocular microscope. And here we followed the methodology developed by Velichko and colleagues. These are the people, the proponents of the desert idea. And we followed their methodology exactly. So we've analyzed our grains exactly as they have. And this method entails taking 50 grains at random from each sample and examining them, looking at how rounded these grains are and looking at how matte or glossy these grains are. And that tells you something about their genesis. And stage 2 of our morphoscopic analysis involved using a scanning electron microscope, is something that Velichko and colleagues have not done. And this is where we took 20 grains from each sample and examined each grain for the presence, absence of various microtextures that are indicative of various deposition and transportation conditions, transportation environments. And by microtextures, I mean things like, you see in these pictures like striations, various fractures, micro pits, cracks, and so forth. And so after doing quite a bit of quantitative analysis, calculating various coefficients, plotting them on graphs, comparing different samples, we came to the following conclusions. That all of the samples can be qualified as fluvial, subsequently reworked by aeolian, meaning wind, and cryogenic processes to various degrees. By cryogenic here, we mean processes associated with freeze/thaw cycles that leave certain types of marks on the grains. And none of our samples could qualify as coming from desert, sandy dune environments. Although 3 out of 7 samples were approaching such environments according to certain parameters. So that tells us that there was significant aeolian action going on in the region, at least in some parts of this region during MIS2, but none of them were intense enough to reach sort of desert conditions. And none of the samples, of course, could qualify as coming from glacial environments. What we also found is that environmental dynamics varied between the 3 regions. And that's not surprising because it's a huge area to cover. So the trend that was suggested by Velichko and colleagues, by our predecessors, that stated that things became sort of more arid and that Aeolian processes intensified during the second half of the period, that trend was only confirmed in one of the cross sections. That's the one that's labeled as number 2 on the map. In the cross section that's labeled as number 1, we actually did not see much change at all from the first half to the second half of the period. So things were quite stable, at least the surfaces were quite stable in this area. And in the cross section that's labeled as number 3, we actually saw the opposite trend of Aeolian processes becoming less intense and the surfaces becoming less arid in the second half of the period. What united all of these sections is that we saw an increase in cryogenic processes, again, the ones that are associated with freezing and thawing in all of the cross sections in the second half of MIS2, which indicates to us the presence of a warm, extended warm period that was conducive to the development of soils, of these cryohydromorphic soils, the remnants of which we found in the wedges. And so to sum up, we think North Siberia during that period, during MIS2, was not a desert, but more likely resembled an Arctic tundra. So it looked, and especially at the end of the MIS2 period, so it looked more like the image to your left rather than the image to your right. And the reason why our conclusions were different from Velichko and colleagues, even though we both relied on morphoscopy, is because we relied on the scanning electron microscope, and its magnification abilities exceed those of a binocular microscope by 100-fold. So we were able to get a more nuanced, more accurate picture of what was going on at that time. But when we compared our binocular data with that of Velichko and colleagues, or with those of Velichko and colleagues, we found that some of their samples must have come from sandy desert environments. Like, for example, they had some samples that had these rounding and matting coefficient values that were in the 90s, and that's quite high. We personally did not have any, did not run into any values like that, any samples like that, but clearly they have. And how do we explain that? Here we need to talk about tukulans. Tukulan is actually a Yakut word that refers to these localized sand dune environments that are encountered in the river valleys of northern Siberia. And they range from a few to 40 kilometers across in size. And they may appear due to various reasons. So, for example, if there was a fire that wiped off the surface vegetation and exposed these underlying sands, then these sands, with the help of wind, may actually travel through the landscape, creating sort of these mini deserts. And I think, or we think that some of Velichko et al.'s boreholes actually landed into such tukulan features that we think existed during the MIS2 period as well. So to frame our conclusion in a sort of more correct manner, we should say that we think Northwest Siberia resembled an Arctic tundra with occasional localized sand dune environments. So thank you for your attention. If you want to take a more detailed look at our data or at this study, you can look up our article online. And thank you for inviting me, and I will take questions whenever the time is right at the end of everyone's talk. Thank you.
Yeah, awesome. Thanks so much, Denis. The way we do questions with these early career talks, everyone, is we'll have a 15-minute section for questions at the end of all 3 talks. But feel free to put your question in the chat if you don't want to have to worry about remembering it and not forgetting it. Otherwise, there will be time for questions at the end. So our next speaker is Sarah. Sarah recently defended her PhD at the University of California, Santa Cruz, where she's currently lecturing for the Earth and Planetary Sciences Department. She's particularly interested in examining grounding line positions in the Ross Sea and how that relates to past climates. Are you all good to share your screen, Sarah?
Yes, I can, sorry.
Cool. Oh no, you're good. All right, go ahead when you're ready.
Cool, thank you. Let me get the laser up and running. Okay. All right, yeah, thanks for having me, and thank you everybody for coming. So yeah, I'm going to be talking to you today about some work that I did as part of my dissertation at UC Santa Cruz in the United States. And this is work that I did with my advisor, Slavik Tulichik. And so the topic of the title of my talk today is Mechanism for the Subglacial Formation of Cryogenic Brines. So first of all, what are cryogenic brines? Well, they are highly concentrated salty water that forms from the freezing of seawater. And this is as opposed to the evaporation of seawater. So you can see chemical signatures of brines tend to fall in this freezing line as opposed to on this evaporation line. Why do we care about cryogenic brines? Well, they are responsible for a significant nutrient flux to the ocean, and they represent a key microbial environment. And then they also have the ability to precipitate minerals that record past ice sheet behavior. And then right now there's a lot of, or for a long time, there's been a lot of interest in trying to find liquid water on other planetary bodies in our solar system. And it's likely that any liquid water we might find on any of those planetary bodies like Mars or Europa or Enceladus, because they're extremely cold, it's likely that the liquid water we find on those bodies is going to be similar to the cryogenic brines that we find on Earth. And so, well, where do we find cryogenic brines on Earth? Well, in the Northern Hemisphere, we find them in boreholes that were drilled into areas that were previously glaciated. So if we look at this figure, this dark black line indicates the extent of the ice at the last glacial maximum. And all these little black dots represent areas or field sites where they have drilled a deep borehole and found cryogenic brines in the pore spaces of those deep boreholes. In the Southern Hemisphere, we find cryogenic brines in the McMurdo Dry Valleys, in the shallow subsurface, and also spewing out of an outlet glacier, so that's Blood Falls. We've also found cryogenic brines in two cores that were drilled in the seafloor just off of Ross Island. So these are the two Andrill cores that were drilled in 2006 and 2007 in the seafloor sediments, as I said, just off of Ross Island. And then we found evidence of past cryogenic brines in the form of mineral precipitates at these two locations here. So previous ideas for how cryogenic brines form required an isolated marine basin. So how does this come about? Basically, you have an ice sheet that forms on a continent, and it's really heavy, so it depresses the lithosphere. But that in turn pushes up the continent in areas where there isn't a heavy ice sheet, and this creates what's called a forebulge. Now, this forebulge can grow large enough that it can actually cut off bits of the ocean from the rest of the ocean. So you end up having seawater that is completely isolated from the rest of the water in this trough that's formed between this forebulge and the ice sheet. So this isolated marine basin is right next to an ice sheet, and it's really cold. So sea ice forms on top of this marine basin. And when sea ice forms, it just takes up the fresh water and leaves the brine behind, or creates a highly concentrated brine that's really heavy. So it falls to the bottom of the basin and percolates into the underlying sediments. So this idea was created to explain the cryogenic brines that we find in the Northern Hemisphere. But I wanted to see if I could take this idea and transplant it to the southern hemisphere and see if we could use this to explain the cryogenic brines that we found in those two andril cores that were drilled. So there we go. So here are the locations of the two andril cores. They were, both of these cores are almost a kilometer long, and or are a kilometer long, and one of the field sites, the water column above the seafloor was about a kilometer, and for the other core, the water column was about 400 meters. And so I wanted, you know, they're already pretty far below sea level. So I wanted to see, okay, is there any sort of sill or moraine or anything that is large enough that could cut those two field sites off from the rest of the ocean? And if you look at the bathymetry of the Ross Sea, it doesn't really seem like it. There doesn't seem to be any sort of area of, you know, shallow bathymetry that, you know, any moraine or sill or forebulge or anything that could have been large enough to cut off, to, you know, create an isolated marine basin over here. But we do find cryogenic brines at these two field sites. So I had to think about, okay, what's another way that we could isolate seawater? Well, at the last glacial maximum, the grounding line was located all the way out here at the continental shelf. And so it's possible that if you have seawater in the sediment pore spaces, and then you put an ice sheet on top of those sediments, then you can cut off seawater from the rest of the ocean and create cryogenic brines. So I wanted to test this idea to see if this is a plausible mechanism for the formation of cryogenic brines. And I did this by modeling the pore water concentration of a sediment column, a 2 kilometer long sediment column, where we have an ice sheet that repeatedly advances and retreats over these sediments. And I modeled the concentration of chloride and also of delta O18 because I suspect that those don't interact with other chemicals and they don't form mineral precipitates. And so the concentration of chloride and also the delta O18 are gonna just tell us basically, you know, exposure to ice and the ocean. So to do this model, I ran an advection diffusion model. So we have our diffusion portion of the equation, and then also I account for density-driven vertical advection because these brines are formed up at the surface and they're relatively heavy. They have a tendency to fall downwards due to gravity. So I consider 3 different surface boundary conditions in this model. I consider, you know, periods of time when the ice is not on top of these sediments. And so the surface boundary conditions are reflective of seawater values. And then when the ice sheet is on top of the sediments, I consider 2 different scenarios. One in which there's freezing at the base of the ice. So in this condition, or in this scenario, fresh water is being pulled from the sediments and added to the bottom of the ice sheet. And so the chloride concentration increases and delta O18 decreases slightly due to the preferential freezing of oxygen 16. And then in the melting scenario, there's melting at the base of the ice sheet. And so fresh water is being added to the sediment pore spaces. And so the chloride concentration decreases and then delta O18 decreases significantly. And so then what I do is I run 100,000-year glacial cycles in this model, and I subject the sediments to periods of seawater, periods of freezing, and periods of melting, and I allow those periods to vary in length. And I run multiple 100,000-year glacial cycles to see if I could reproduce the profiles that we found in the observed profiles for chloride concentration and delta O18. And sure enough, I was able to reproduce both the chloride concentration and the delta O18 for both of these cores, which indicates that this is actually a plausible mechanism for the formation of cryogenic brines. It is possible that you can form cryogenic brines in the sediment pore spaces underneath an ice sheet. One thing I want to point out, though, is these two field sites were very close. They were very near each other. Yet, if you look, I was able to reproduce the chemical profiles for the Andro 1b core in 600,000 years, so 6 glacial cycles. But the other core looks like it took about 19 or almost 2 million years to recreate the profile seen in the Andro 2a core. So, that seems a little counterintuitive or seems a little odd. But if you look at, if we remember that one of these field sites was much more shallow than the other, then we can explain, the difference in the number of cycles that each of these field sites were exposed to. So, the Andro 2a core was only about 400 meters below sea level. And so it's possible that there were scenarios in which there was enough, climate cooled enough that the ice shelf was able to thicken enough to ground on the Andro 2a field site, but not on the deeper Andro 1b field site. And so based on that, it's possible that this particular field site has just experienced more grounding events of the ice shelf. And this is, is reflected in the temperature history for this. This is a temperature proxy for global mean temperature for the last 5 million years, but we're only interested right now in the last 2 million years. And you can see that the earlier fluctuations are much smaller than the more recent fluctuations. And so it's possible that during all this time, the ice shelf was able to thicken enough that it could run aground on the shallower field site, but it took until the more recent larger temperature fluctuations for the ice shelf to thicken enough to ground on that deeper field site. So in conclusion, it is possible to form cryogenic brines in sediment pore spaces, and this is really useful for the Ross Sea because it doesn't require an isolated marine basin, which is very hard to justify in the Ross Sea. And then cryogenic brines may be more prevalent underneath the Antarctic ice sheet than we currently know, because it's likely that there are brines hidden in the sediments where the Antarctic ice sheet is frozen to the bed. So if we look at this figure over here, the blue indicates where the ice sheet is frozen to the bed, and then the yellow indicates areas where there is melting at the base of the ice. And you can see that the areas that we've either found cryogenic brines or we found evidence of past cryogenic brines seems to align with areas where there's freezing to the base of the ice. And so if we were to drill into any of these other areas that are indicated in blue, we would probably find cryogenic brines in the sediment pore spaces underneath the ice. And then if we go back up to the northern hemisphere, right now, all the areas that we've found cryogenic brines, we've just been drilling in areas that are currently on land. But if we were to drill into areas that are currently covered by the ocean, but at the last glacial maximum were covered by ice, we might also find cryogenic brines in the sediment pore spaces there. Thank you very much.
Awesome. Thanks so much, Sarah. Again, if you have any questions for Sarah, feel free to put them in the chat or hold on to them until our question and answer session at the end. Our final talk of the 3 early careers this morning is by Brianna. She's a PhD candidate at Colorado State University in the Geosciences department. She's interested in characterizing ice-marginal lake change in Alaska and their relation to glacial lake hazards. She's also interested in mountain permafrost and rock glaciers in the Rocky Mountains. Go ahead, Brianna.
All right, thank you for that introduction. So I'll be presenting on the research for one of my dissertation chapters, which can currently be found in the cryosphere discussions. Before I get started, I'd like to thank my collaborators for making this research possible, in particular my advisor, Daniel McGrath. All right, so ice-marginal lakes are located adjacent to glaciers, commonly forming at glacier termini, tributary junctions, along glacier margins, or where glacially eroded bedrock or sediment creates topographic depressions. These lakes can be dammed by moraines, bedrock, glacier ice, landslides, or by surface topography, often created by glacier debris cover. So depending on lake location and societal factors, these types of lakes can have a large impact on local societies and ecosystems, ranging from water resources and tourist attractions to altering sediment flux within a basin, and as well as wildlife habitat. These lakes can pose a great risk if they drain suddenly, producing a glacial lake outburst flood or GLOF. So inventories of ice-marginal lakes serve as a critical first step in understanding where lakes are located on the landscape, as well as how they're evolving for water resources, habitat, glacier dynamics, as well as GLOF hazards. A region-wide inventory of ice-marginal lakes in Alaska has not previously been conducted, particularly one which characterizes lakes by dam type. Other regional studies have documented different trends depending on dam type. So we decided that this was an important factor to consider within our inventory. The idea here is that if we solely report the total change in number and area of lakes, we may miss important trends between the different dam types. For example, moraine dammed proglacial lakes tend to be larger and expand with glacier retreat, whereas superglacial lakes tend to be small and have a large spatio-temporal variations. So the goal of our study was to create a multi-temporal inventory of ice-marginal lakes in Alaska to document decadal scale changes in lake area, as well as characterize these ice-marginal lakes. So our study area covers region 1 of the Randolph Glacier inventory, which includes all of Alaska and a bit of Southwest Yukon and Northwest British Columbia. This region has the second largest glacier extent outside of the ice sheets and spans a wide range of climates and geologies, which makes this region really interesting to study, but also makes it a little bit more challenging to characterize. So in order to create our inventory, we used a combination of supervised classification and thresholding methods. We used 4 different time steps within our inventory, creating 5-year mosaics in the 1980s, 1990s, 2000s, and 2010s. We created these cloud-free mosaics in Google Earth Engine using imagery from Landsat 5, 7, and 8. After classification, we used a series of thresholds to minimize the inclusion of false positives created by things such as mountain shadows, as well as wet superglacial debris bands. We then manually verified all of the polygons and visually classified each lake by dam type and topological position. So for dam types, our classifications were moraine, ice, superglacial, and bedrock. Because all of those are a bit self-explanatory, with the exception that all the superglacial lakes that we identified were located within glacial debris cover rather than on clean ice. Our classifications for the topological position were proglacial, or at the front of the glacier, superglacial, on top of the glacier, detached, meaning in front of the glacier but no longer in contact with the ice, unconnected, meaning there's no glacial influence, and then lakes that were dammed by ice. So we included unconnected lakes because our definition of an ice-marginal lake for this inventory was any lake within 1 kilometer of the RGI outlines. Just a little side note, unfortunately, due to the use of our supervised classification for lake identification, we could only identify lakes which appear spectrally. So this results in the exclusion of some ice-dammed lakes, which are either iceberg filled or spend the majority of the summer drained, as they do not appear in the 5-year mosaics. Therefore, we're presenting this as a clear minimum of ice-marginal lakes with a few known false negatives. For example, Suicide Basin, Valdez Lake, and Snow Lake, as well as a couple other. And these lakes, which have experienced multiple drainage events, are important for individual GLOF hazard assessments, though we believe their exclusion has a minimal impact on our assessment of decadal scale trends by dam type. So getting into the results, in total, 791 individual lakes were identified within the Alaska region. Overall, the total number and area of lakes increased over the period of study, adding 176 lakes and 467 kilometers squared in lake area. So this chart shows number and area of lakes colored by dam type, with green as bedrock, blue as ice, pink as moraine, and purple as superglacial. Lake number and area do not directly correlate across dam types. For example, moraine dammed lakes compose 40 to 44% of lake population, but make up to 79% of total lake area, whereas superglacial lakes make up 16 to 23% of the population, but only contribute 2 to 3% of the total lake area. So looking at changes over time broken down by dam type, we see that bedrock, moraine, and superglacial lakes all increased in number and area. However, ice dam lakes decreased in total number and area. These decreases are likely due to the thinning of ice dams or changing of subglacial conduits. So this decrease is one of the most important or interesting results from our study, as ice dammed lakes, particularly in Alaska, are known to commonly drain either every year, every couple of years, and therefore, depending on the trends of individual lakes, this result could have implications for gulf hazards from ice dammed lakes. We also calculated the total area change for each of the 791 individual lakes within our inventory. And this plot shows the distribution of individual lake change by dam type, showing results for all lakes in the darker curves and only lakes with detectable change in the lighter curves. We considered a lake to have detectable change if the area change was greater than the calculated error for the lake outline, which we use plus or minus 1 pixel. So again, the main takeaway from this plot is that ice dammed lakes have a negative median change, whereas all other lake types have a positive median change. This trend in ice dammed lakes would not have been identified if we had not considered dam type within this study. So this next plot displays the frequency of lake area in the bars, with lake area on the x-axis and number of lakes on the left y-axis. The solid line represents the total relative cumulative sum of lakes, and the dashed lines represent the relative cumulative sum of total lake area and lake area difference. So we see that lakes less than 1 kilometer squared compose over 75% of the lake population, whereas they contribute to less than 15% of the total lake area. On the other hand, lakes greater than 10 kilometers squared make up over 60% of the total lake area and area change in the region. The majority of the lakes greater than 10 kilometers squared are also moraine dammed. So a fairly unique feature in Alaska is the presence of these large proglacial, often low-lying lakes, often near the coast. Some of these lakes have experienced massive changes in the area over the past couple of decades. For example, the proglacial lake at Grand Plateau Glacier has expanded by almost 20 square kilometers since the mid to late 1980s, and Harlequin Lake at Yakutat Glacier has expanded by nearly 43 square kilometers. These examples again demonstrate the importance of tracking individual lakes through time, acknowledging that these sorts of lakes dominate the total regional lake change signal when considering the region as a whole. So unfortunately, I don't have enough time to go into too much detail, but this map shows an overview of where all of the ice-marginal lakes in Alaska region are located, colored by dam type and separated by RGI subregion. Superglacial lakes are most common in the Alaska ranges, which have the highest percent debris covered, followed by the St. Elias Mountains. Ice dam lakes are also most common in the St. Elias Mountains, whereas bedrock and moraine dammed lakes dominate the West Chugach Mountains, as well as the North Coast Ranges. So as temperatures continue to rise and glaciers thin and retreat, ice marginal lakes will continue to change. As Alaskan glaciers have retreated off their Little Ice Age moraines, it's unlikely that new moraine dammed lakes will form. However, proglacial lake expansion will likely continue as glacier retreat accommodates lake growth, of course, depending on basin geometry. Alaska's glacier complexity and relative abundance of ice-dammed lakes also poses an interesting question as to whether these lakes will continue in their trend of decreasing number and area, or whether new ice-dammed lakes will form if ice in tributary valleys retreats faster than main branch ice, similar to what has happened in Suicide Basin since 2011. This could have huge implications for future Gulf hazards, and modeling basin geometry and future ice extent would provide insight into this question and help predict where future ice marginal lakes might form. So to wrap things up, I'd like to reiterate that we found that overall ice marginal lakes in Alaska have grown in both number and area over a period of study. Moraine dammed lakes are growing at the fastest rate. Ice dammed lakes have decreased in number and area. And again, this study demonstrates the importance of dam type and topological position in regional ice marginal lake studies. And this is just a first step in understanding ice marginal lake evolution and dynamics in Alaska. So if you'd like more details or want to read more about this work with much further analysis, a link to the paper is in the bottom of this slide. The data set is also publicly available at arcticdata.io. So thank you all for attending today. And next week's speaker is Ralph Griff, giving a talk called Of Cold Ice, Warm Ice, and Water, Thermodynamics of Ice Sheets and Glaciers.
Awesome. Thanks so much, Brianna. I'm going to turn it over to Sammy, who's going to run the question and answers, but it looks like there's already a question in the chat for Brianna from Roger, if you want to tackle that one while Sammy gets on here. Thanks so much.
Thanks, Lauren. Roger, do you want to ask your question out loud?
Yep, sure. Thanks very much. Thanks to all three speakers. Enjoyed all those, particularly for Brianna. I was just wondering if you have a sense of how much earthquake activity has modified any lake areas, even over the time period you're looking at. I'm sure there's been some pretty big magnitude 7s and so on that will have changed the geomorphology and drainage and so on.
Yeah, I would believe that earthquakes have impacted it. Unfortunately, that's not something that we have looked at thus far. I feel like now that we have this first initial data set, there's a lot of different directions that we can go in and trying to understand exactly why there are these changes, or if there's changes in specific regions. But yeah, that's definitely something to look at. So thank you for bringing that up.
No worries. Thanks very much again.
If we have any more questions, feel free to unmute yourselves. There's quite a small number of people today, so. Just going to check if we've got anything on the Facebook as well. Otherwise, I do have some questions. Okay, also feel free to drop questions into the chat. If you aren't able to unmute, I'm happy to read them out for you. I can see Roger has another one, so please go ahead, Roger.
Yes, thanks very much. Thank you, Sarah. That was interesting. Do you know of any work on the geophysical properties of the postulated cryogenic brine-filled sandstones? I'd be interested to know what they would appear like seismically, for example, or perhaps to radar, given that instead of slow water, you've got fast ice in p-wave velocity terms. in the pore space. It's the kind of thing a reformed oil industry rock physicist ought to look at.
Yeah, that's a good question. I don't know much about the geophysics, but I do know, so the cryogenic brines that we know of in the dry valleys, we know that from ERT stuff. So there's yeah, they've flown it's called a SkyTem, which is this Danish like big coil that can measure like salty water underneath the surfaces. So we've done that for the dry valleys, and they're very salty.
Yeah, it's an electromagnetic system, a bit like mine detection in ships and so on. It's going to look for electrical conductivity. Yeah, smashing.
Yeah, but I don't know about seismic.
No, I'm just intrigued because I imagine if you've got a sandstone that's got water in it, it will be seismically relatively slow, a bit like the speed of the quartz grains plus the water. But then if you replace the water with ice, it's going to look very fast seismically and potentially be confused at a crude interpretation of seismic data with something else. But it doesn't detract at all from the excellent work you've done. Thanks very much for your talk. Enjoyed it.
Thank you. Yeah.
Okay, thanks, Roger. I can see Hongji Shi, you've got a hand up. If you want to go ahead and ask yours.
Yes, very interesting talk. Thank you very much. This is Hongji from University of Texas, San Antonio. I have a question for Brianna. The last talk, very interesting result. I see overall the area and the lake number increase, but some of them actually increase, but others decrease. So I wonder if you have any explanation why some of them actually decrease. Thank you.
Yeah, so the question is why some of the lakes would be decreasing in area?
Yeah, in number and in area, yes.
Mm-hmm. Yeah, so the ones that decreased were ice dammed lakes. And so the thought is that if you have ice and then a lake behind it, as the ice is thinning, then that decreases the overall volume that dam can, the amount of water that can be held behind that dam. And if either the ice disappears or if there's a new conduit underneath the glacier, then it may no longer hold that water anymore. And so it's mainly just where there are ice dams that we see these decreases in area or the disappearance of the lakes.
Okay, that's good. Thank you.
Yeah, I can see we've got a question from Doug as well. Doug, do you want to read it out loud for the benefit of people watching this back later?
These are absolutely wonderful talks. Thank you so much. My question is probably pretty naive, but it seems like the first talk by Denis and the second talk by Sarah both were looking at the paleoglaciology of the Northern Hemisphere. And I'm just wondering if some of Sarah's methods might be applicable to the questions that Denis is looking at. So I'll just leave it at that as my question.
I think it would be really interesting to see what this method, would produce in our area. But I don't have any more specific comments on this.
Yeah, I agree with that. I think it would be, or to even just look to see if you find cryogenic brines in areas that were believed to be not under ice.
Well, thank you. And again, really great talks.
Okay, thanks, Doug, for that potential future collaboration opportunity. We've got a question come in on the Facebook from Joanna Young. This is for Brianna. And Joanna says, I'm wondering whether there is a way to track those ice-dammed lakes that are iceberg filled and or that experience seasonal drainage. Just curious if she sees a way forward in inventorying those as well.
Yeah, so that's something that I'm actually interested in looking at the next step. So there, yeah, it takes a little bit more, it's harder to do completely automated spectrally. So I've been looking at them visually of either lakes that I know exist that were not identified in my inventory, and then going through and creating kind of almost like a time lapse of those and using kind of every image available. Also with the drainages, those happen at a shorter time scale than the kind of 5 to 10 year scale that I was working with. And so that's part of why they weren't identifiable in the inventory. But yeah, that's kind of the next step, is hopefully to use almost every single image to be able to look at those changes over time.
Great, thanks, Brianna. I should say that Joanna's also put on the Facebook that you really enjoyed the talk, so thank you, speakers. So I guess you're not all monitoring that as well. Do we have any more questions from people in the Zoom? Okay, well, I'm going to take the advantage of asking Dennis a quick one then, and while everyone else is still thinking. Dennis, I was wondering if there are any other areas you think you could apply your methods to, where maybe things may have been misclassified in the past, or there's more to learn about particular areas. If you could take your research anywhere worldwide, where would you go next?
This type of research, thank you for the question, Sammy. This type of research has been done in a lot of areas already, starting in about 1970s. But I think it was done sort of disproportionately, and I'm talking about morphoscopy, and especially about the morphoscopy that uses the scanning electron microscope. It was done mostly in Western Europe. And so these Siberian environments are quite different because our climate is drier, more arid in general. We have less snow, and we have, less conditions for the formation of glaciers. We actually need to do more research in sort of the eastern part of Eurasia. I wish we need to expand sort of our database, of these different microtextures, because it's all statistical. You take a bunch of parameters from your samples and compare them to what's already been published. Well, what's already been published mostly comes from, like I said, Western European contexts and other contexts that work in the context of glacial, periglacial environments and so forth. But in Siberia, we have these very low temperature environments, but we don't have, and in the past didn't have widespread glaciers like they were in Europe in those areas. And so I couldn't get a close match. I couldn't get a perfect match between my samples and anything that's been published out there. So I think we need to work on sort of developing a larger database for our region and just testing different sites in our region, and just in general different areas all over. Wherever there is sand, and there is sand just about everywhere. So this method applies just about everywhere.
Thanks, Dennis. We have any more questions from the Zoom? Oh, I can see we've had one in from Roger again. Roger, do you want to ask that one?
Sorry, just a comment, actually, curiosity. You showed those lovely sets of histograms, Brianna, with all of the results broken down by different type and so on, showing that the ice one was largely different. But there was a sneaky little extra peak on the opposite sign of change. I just wonder, what was the rogue lake that produced an increase rather than a decrease?
For the ice dammed lakes?
Yeah, you had that lovely slide with all the different histograms arranged vertically, I mean,
Let's see
maybe
if I
I want to
can.
roll back to it, but
Yeah, let's see which one.
back. That's it. That's the one.
Oh, this one.
Oh, that's it.
Oh yeah, the
on
little.
the ice one, there's a sneaky little extra peak that didn't behave.
Yeah.
Who was the rogue one?
I don't know if I remember specifically which lake, but there are some instances. It really depends on the basin geometry, because there are some where if the ice is retreating in that tributary valley, depending on the geometry, that could still be increasing the area. It really depends on that geometry. So, but I'll have to look into that.
Yeah, it's just a kind of annoying little extra outlier that confounds your simple statistics when you try and give a bullet point answer. But yeah, smashing, thanks.
Yeah.
Thanks, Brianna. Taylor's made a comment in the chat as well that I'll read out for benefits of those who aren't looking at the chat. It's a reminder that before next week's session, we'll have a 20-minute chat session. It's happened today. It was really nice to get to talk to people informally before the seminar. Feel free to bring cake, coffee, tea, beer, or wine as suits your time zone and meet some colleagues informally. Or you may turn up expecting to have a chat and a glass of wine and instead get asked to chair the questions at the end of the session, as happened to me today. So be prepared for that one, but don't let that put you off. We've got a couple more minutes left before we get to the hour if anyone has any final questions. Oh, I can see we've got one actually on the Facebook from Hester, and it's a question for Sarah. Sarah, can you explain if you can differentiate between sea invasion brines and brines that leach from pre-glacial sediments? And she's put in brackets, basinal brines, e.g. Mesozoic marine shales, that may be glaciotectonized affected by subglacial hydrology. I'm also going to paste that into the chat for you, Sarah, because I think I read that one out pretty terribly.
Thanks. Yeah. Okay. I don't know that I can tell the difference between brines that come from the ocean versus ones that leach from sediments, but that is why I actually chose to only look at Delta 18 and chloride, because I don't believe that those came from the sediments at all. And so those should have just come from either the ocean or from the ice. And so there are other chemicals that were measured, or ions that were measured in the pore waters that I ignored because I didn't want to have to worry about that exact process. I didn't want to have to worry about precipitation or dissolution of minerals. So that's why I stuck to chloride and Delta 18.
Thanks, Sarah. I think we're probably at the point of wrapping up now. Is there anything else any of the organisers want to add before we finish up? Okay, I'm guessing that's a no. But yeah, well, I'd like to echo what a few people have been saying in the comments on the Facebook. Thank you to the speakers. They were such a really good set of talks and all stuck beautifully to the time as well. I think the early career talks are sometimes the very best ones in these seminars. So thank you, everyone.
Yes, thank you so much to all the speakers, and thank you so much for the chairing. It was nice to be able to listen without diversion, so to speak. So thank you so much.
Thank you guys for having us.
Yeah, thank you.
Great seminar.
Thank you.